Okay guys, how's it going? We're going to finish off with another activation energy video. We'll probably do a plot after this and then we'll call it for the Arrhenius equation. Let's get started with this question. So again, we are in kinetics nearing the end of the chapter. So number 23, if the activation energy for a given compound is found to be 103 kilojoules per mole with the frequency factor of that number we see, what is the rate constant for this reaction in 398 Kelvin? Okay, so what do we do here? Well, we need to remember an important equation. So, we've been saying a lot of stuff like rate equals K, and we have like rate orders like to the M power. But what is this K that we've been talking about this whole time? Well, K actually has a lot of things, a lot of variables rather, that compose this particular constant. And now we're actually going to derive where all these come from and what they mean. So K is actually, let's take a look, it's actually A, which is another variable, e to the negative EA over RT. So there's actually quite a bit of variables involved in this. And then A is going to be composed of two other variables within it that are the frequency factor and the collision factor, which we're not going to talk about in this video. We will just plug in the value that they give us here. They did happen to give us the frequency factor that you see here, which was given in the question. So we don't have to worry about that just yet. Okay, but let's take a look. What do all these other variables mean? So let's wrap them up. So A, we said, was our frequency factor. T was going to be our temperature. That's going to be in Kelvin. R is going to be the thermodynamic constant, that 8.314. That's going to be joule over mole Kelvin. And EA is going to be our activation energy. Okay, so we have all of our components of this equation, and now we can solve for it. However, we do have a lot of other things we can do in this equation. So what are we solving for in this case? What is the rate constant if the reaction, what is the rate constant for this reaction at 398 Kelvin? So fortunately, we're in a position that because we have all of the components here, we can just plug it in and solve for K. Now, if we had to solve for one of the other components, we would have to get some algebra in here and start getting natural logs and moving around some variables, which we will probably do in the next video, because that's going to be important in that video. But in this particular video, we're kind of going to be plugging just some values in. But let's do that really quick. Okay, so let's solve for K. That's what we're solving for, the rate constant. So we have our K equals our A, which is our frequency factor, which is given to us, which is 4.0 times 10 to the 13 reciprocal seconds. That's going to be 4.0 times 10 to the 13 reciprocal seconds. To the E, our negative EA. So our activation energy is EA, as we said before. Activation energy is given to us as 103 kilojoules per mole. Well, let's consider this. Our rate constant, R, is in units of joules per mole Kelvin, and our activation energy was given to us in kilojoules. So we need to switch one so the units can cancel. So what I'm going to do is just adjust this to 103 times 10 to the 3 joules per mole. And why I did that, just because we know that for every 1 kilojoule there is 1,000 joules because of the metric system conversion. So that's my EA, and we're gonna remember to put the negative in front of that. It's important. Over R, which is my rate, my thermodynamic constant of 8.314 joules over mole Kelvin. And finally, my last component, which is temperature, which is at 398 Kelvin. All right, and we have our answer here, so that's going to be K. So let's figure this out. Let's actually cross out some units while we're at it too. So my joules here, let's see, that's joules over mole. So these joules are going to cancel. See, the moles will also cancel. And I'll be left with just temperature, as we see. Joules over mole Kelvin. Actually, the Kelvin will cancel as well. So cool. So I'll write it really quick on the side. So it's joules per mole over joules over mole times Kelvin times Kelvin. Which says over 1 basically. So we can cancel the kelvins, the moles will cancel, and the joules will cancel as we see. So all we have at the top then is just some unitless number at the top. So cool. Hopefully that was some quick clarification. Okay. So now we have to just solve for K. Given these numbers, this might take a second because this is a fairly large number we see. So let me plug that in. So for K, we have, let's see, so it's 4.0 times 10 to the 13th power, multiplying that by E, and that's going to be multiplied to the, let's see, put a parentheses in there, a negative 103 times 10 to the 3rd power over another parentheses, 8.314 times another 398. We forgot we did put our negative in there, so we're all set. And our answer at the end, K, is equal to 1.212. Now, let's look at our options and look at our significant figures. Looks like 2 sig figs is what we're grinding to, so that's K. It's going to round to 1.2. And remember, all the units canceled up top, so all I'm left with is seconds to the, or rather reciprocal seconds. Well, that's my answer. Let's take a look at our options. It looks like our answer is A as a result. Cool. A fairly easy question because we're just plugging in our values into this equation. But this does get a little different when we're linearizing this equation. And what I mean by that is getting the natural log and making it look like the form of y equals mx plus b, which is what we're doing in the next question. Let's go to that right now. Shown below is an Arrhenius plot for the reaction that we see here. Based on this information, determine the activation energy and the frequency factor for this reaction. Estimate your calculation to 3 significant figures. Make sure to pay attention to this video. You will see something like this most likely on the exam, so it's worth taking the time to understand it. So we're given a graph, and we're given an approximation of the formula for the line. That's just like a linear regression, so that's y equals negative 16108 x plus 23.271. It's a little hard to see over there. So, okay. So that's our slope right there. The slope is going to be this negative value that we see here. So that's our m. And this is going to be my y-intercept here. That's just the, as we've discussed before. Okay. So how do we do this? Well, in order to determine which parts are which, we need to linearize the Arrhenius equation. And before, remember, just to recall, the Arrhenius equation was that K equals the active, the frequency factor, e to the negative EA over RT. So we need to get the natural log of both sides to linearize this graph. So that's going to be the natural log of K equals the natural log of A e to the negative EA over RT. Remember, this is a product in between here, so we can separate that into addition. So it's going to be the natural log of K equals ln of A plus ln of E to the negative EA over RT. When we do that, getting the natural log of E will cancel out the natural log in that. So we're left with just ln of K equals negative EA over R T plus ln of A. Okay, we're almost done. So the variable that's going to be changing in this is going to be the temperature. So we're going to pull that out. So it's going to be the natural log of K equals negative EA over R times 1 over T plus the natural log of A. And we have our equation. So let's take a look at what we got here. So which part of this equation is analogous to y and mx plus b? So let's take a look. So the natural log of K is going to be the y. My slope is going to be this negative EA over R. And x is going to be 1 over temperature. and my y-intercept, b, is going to be the natural log of a. Great. So we have all of the components that we need to solve this problem. We derived the equation ourselves. So now let's rather look at the question and see what they're asking for. Based on this information, determine the activation energy, EA, and the frequency factor, A. Estimate your calculations to 3 significant figures. So they want the frequency factor, which is A. So let's look at the equation that they wrote. So y is equal to negative 16108 x plus 23.271. Well, based off the equation we wrote, we said that the natural log of A was A is our frequency factor. So then this ln of A, we can essentially equate this to the 23.271 to determine what our frequency factor is. So let's do that. So then the natural log of A equals 23.271. We're essentially equating the two equations because that's the part that is, that's analogous to the other. Great. So we're not done yet because that's the natural log of A. So if we raise both sides to the e power, e to the ln of A, and e to the 23. Well, the e and the natural log will cancel, and I'll be left with A equals e to the 23.271. Well, let's solve that. Let's plug that in. So our value e raised to the 23.271. They said they wanted this to 3 significant figures. So our answer is going to be 1.2, I'll write the whole thing, 77 times 10 to the 10th power. Well, we're going to round this to 3, so it's going to be 1.28 times 10 to the 10th power. So that's going to be our A. And we solved for our frequency factor. Okay, so now we need to do the same thing for the activation energy, which we said was EA over R. Now in the equation above, that was 1.6108. So we're going to equate these two slopes to each other. So when we do that, we get, let's see, that's negative EA over R equals negative 1.16108. Okay. Remember, we're solving for EA. So for one thing, these negatives are going to cancel each other out. We'll get rid of those, multiplying both sides by R. And these cancel. My EA is going to be equal to 16108. And remember that R does have a value, and that was the 8.314 value. And we are done. So we have to just plug this value in. So it's going to be 16108. I'll be multiplying that. 8.314. The answer we get is EA. So remember, normally this is in joules. So this is going to be, this is going to be in joules, but let's put this guy into kilojoules so it to be a little bit smaller. So let's divide that guy by 1,000. So we're going to have a total value of 133.922 kilojoules per mole. Now, I'm going to round this to 3 significants. That's the question demanded. So that's going to be EA equals 134 kilojoules per mole. All right, so we have our answers. Let's do a quick recap on how we did that. We derived from the Arrhenius equation. We were able to linearize it by getting the natural log of both sides. And then given once we linearized it, we were able to equate the components of to the linear equation that they gave us above. To solve for the frequency factor, we equated the natural log of A to the point that was analogous to it in the linearized, the linear regression given to us in the problem. So all we do is equate those points, and once we do that, we can solve for our components fairly easily. I hope this was helpful. This is something that you will absolutely be expected to be able to do on the exam. So be prepared for that. Go over this problem again and find others that are similar to it. I hope this was helpful, and I hope you have a good one.